This video is on related rates for calculus. This is the same as section 4.1 in the book. I really recommend you read the section of the book. It's only a few pages, though it could take you a while to really understand it, work through the problems, their example problems. That will really help, and I'll try to do the same thing here, and then hopefully you get a really good grasp of what's going on. So, related rates is a perfect name for these problems because they are relating rates. It's nice when names are right. Basically, you know how fast one thing is changing, and then you use some geometry, some math relations to figure out how fast another thing is changing, and you do that usually with taking the derivative implicitly. It's all about using your implicit derivative skills with respect to time, since it's time that's changing. So it's always with respect to time. So as always, usually the best way, that's good. The best way to see this is with an example. And this is similar to the example in the book. I'm going to change it a little bit. So let's say we have a ladder. I'll make my ladder green. You can see that. We have a green ladder leaning up against a wall, and let's say the ladder is, let's say 12 feet long. We'll just do everything in feet. And let's say you know that this top point, it's sliding down the ground, so the ladder's sliding down, hopefully you're not on it, and the top part right here is always falling down at, let's say, 3 feet per second. Okay, so it's falling down at 3 feet per second. So that's the rate that we know, and we can call this y, and we can call this x, because that makes sense. So then what we want to know is how fast is this point moving along the wall. And since that's the rate of change of x, we can call that dx dt, the rate of change of the x position. We know the rate of change of the y position, which is dy dt, so we can write dy dt is equal to 3, and we'll just make sure everything's in feet, and we don't have to write feet all the time, feet in seconds. So what is dx dt for a 12-foot long ladder? So what we have to do then is relate y to x. In this case, that's pretty easy. You just use the Pythagorean theorem. So x squared plus y squared is equal to the hypotenuse, which is 12 squared, which of course is 144. And then we need some dx dt's and dy dt's. So what we do is we take the derivative implicitly. So you say we take the derivative with respect to time of everything. How fast these things change with time. Okay, what I'm going to do is use notation that actually Newton used, and it makes it a lot easier. He said, just to make things simpler, let's notify the rate of change of something with respect to time, since that's really common, as the coordinate value, the variable with a dot over it. Instead of writing dx dt, just put x dot. So dy dt then, of course, would be y dot. And it's just like before when we said dy dx. Instead of writing dy dx all the time when you're doing math with it, that gets kind of tedious, so we can write y prime, and we know that's dy dx. Now we're just going to use the dot thing for dx dt. It only refers to t's and just makes it so much easier. So again, just like the prime, but we're going to write dots, which we know is respect to time. So let's take the derivative of this implicitly. The derivative of x squared, derivative of anything squared is 2x times the derivative inside time, which makes it x dot, just like before. Because it's always respect to time, so x isn't any more special than y now, because it's respect to time. Then, derivative of y squared, which is the exact same thing, y dot, 2y squared is 2y times the derivative of what's inside with respect to time, which is dy dt, which is y dot, equals the derivative of 12 squared, the 144, which is 0. Okay, what we want is x dot. We know what y dot is. And we need to know, okay, so let's solve for x dot. The 2's are going to cancel, divide both sides by 2. So x dot is equal to, x dot is equal to negative y dot, or how fast the x variable is changing, dx dt is negative y dot divided by x. So if we want to know how fast the x is changing, we need to know at what point how big is y when it's changing? How big is x when it's changing? Because it's gonna change. When the ladder's just about to hit the ground, that point's going to be changing. When the ladder's like right here, that's going to be changing differently than when it's way at the top and just starting to slide. Even though the top is going down at 3, how fast this is going to change depends on where the ladder is. So to solve this problem, we have to say, okay, when y is a certain value, when x is a certain value. Okay, so let's do that. So let's say that we want to know this happens when y is, I don't know, when y is 6. Okay, when y is 6. Now then we also need to know what is x when y is 6. So let's see. So we have x squared plus y squared is equal to 144. When y is 6, that would be x squared plus 36 equals 144. X squared is 144 minus 36. Can I do that in my head? I think that's 108. 108. So x then is a square root of 108, which is not going to be a pretty number. Let me figure that out. So 108 square root is 10.4. So about 10.4. And also notice this is negative. Our x dot is positive. It's going in the positive direction. But when I said the y dot is 3, really it's negative 3, right? Because y is going down. So to get the math right, I should say negative 3. So now we can plug in all these numbers. The y value we said was 6, so it would be negative 6 times y dot, which we said was negative 3, divided by x, we just figured out is 10.4. Again, that's how fast the x is going to be increasing. And so that's what, 18 divided by 10.4? So I get 1.73. So it'd be 1.73 feet per second. Okay, so that's how you solve these things. You draw a good picture. Always important to draw a really good picture. Label the things, put letters on it. Obviously, when you know y in the up and down, x sideways, do whatever letters kind of make sense to you. Write down, okay, the numbers here, that's 12. Figure out what relation is going to relate things. In this case, it's the Pythagorean theorem, obviously relates them. Take the derivative implicitly with respect to time. So that means x and y aren't any special to each other. It's not prime, it's dot, because with respect to time, so the derivative of 2x is 2x x dot. And then solve for what you want, and then figure out all the other things that you need to know to get the final answer. Okay, so to help you with these problems, again, you have to relate things, which means they're basically geometry problems. It's geometry, relating things, and then using implicit differentiation to then solve for what you want. Okay, so what are ways to relate things? One of them, like we just did, is the Pythagorean theorem. X squared plus y squared equals the hypotenuse squared, call it d or something, is d squared. Another one that you'll commonly use are similar triangles. Like if we have a triangle over here, and then we also have a triangle inside it. Let's call this side here A is the small width, and this is B, and then we'll call this whole thing C and D. Then we can take the ratio of their sides of the same triangle. So A, the little one and the big one are similar triangles. So we can say that A is to B, this side is to that side, as C is to D. That's often a way to, something you can use to relate things using geometry. Let's see, another one that often comes up is trigonometry. They did an example like this in the book, like, you know, tangent theta is what you want over the other thing. So if we have our triangle here, and here's theta, let's call this side A and this side B. Tangent theta is opposite over adjacent is A over B. And of course you could use sine theta or cosine theta, whatever one makes sense, whatever one works for the problem. So it's always about drawing the picture and then using some kind of relation to relate the things that you know. You're always given one of them, you take the derivative with respect to time, then to figure out the other one by getting all the different dots. So let's see, a couple more that you can use. Our volume formulas, if you want to know how the volume is changing. So like, you know, for a sphere the volume is 4/3 pi r cubed. So volume formulas. And then the other ones often used are area formulas. So like the area of a circle is pi r squared. So area formulas are often used to relate things. It all depends what you're trying to do. Let's do a quick area one here because they're kind of easy. Let's say that we have a circle. Okay, so here's another example. Let's say we have a circle and it's expanding. It's getting bigger, like it's a puddle of water that's getting bigger, water's leaking into it. Let's say it's getting bigger by a dot. The area of the circle is increasing by, let's say, 10 centimeters squared per second. Always increasing by that. So here's our radius. So let's say we want to know what a dot is when the radius is 4 centimeters. When the radius is 4 centimeters, the a dot's always 10. When the radius is 4, how fast is the radius increasing? So what is r dot? How fast is the radius of the circle getting bigger when the radius is 4 centimeters? And the area is always increasing by 10. So we write down the formula for the area of a circle. A is equal to pi r squared. We take the derivative with respect to time of this whole thing. Derivative of a is just a dot. That's the easiest thing. If this is by itself, it's just dA dt, which is a dot, equals pi times the derivative of r squared, which is 2r r dot. We want to know what r dot is. So r dot is equal to a dot divided by, let's see, 2 pi r, right? Because we have a 2, an r, and a pi that go on the other side. I think I did that right. Now we can plug in the numbers. A dot is 10. Then divided by 2 pi, and we want to know when r was 4, so divided by 2 pi times 4. So that is 10 divided by 8 pi, 10 divided by 8 divided by pi, and I get 0.397, yeah, let's say 0.4. So it's about 0.4, and since we're dealing with centimeters, we know that's centimeters per second. So the radius is increasing at 0.4 centimeters a second at that time. Okay, those are some examples. Again, look at the book for more examples of how you do these related rate problems. I think they're really fun. It's kind of a fun application of geometry and calculus. So good luck with these. Bye.